elastic behavior materials. We talked about some of the different effects of microstructure on Monday, polymers and cellular materials. Today we're going to do a quick introduction to elastic behavior composite materials. So I'm sure most of you know a composite is a mix of two or more distinct materials. They are both man-made and natural composites. Wood, bone, teeth, seashells, those are all natural. Man-made fiberglass, carbon fiber epoxy, or fiber reinforced. You can have a variety of matrix and a variety of what we'll call reinforcements. And these can be polymers, metals, ceramics. They can have different geometries. They can be fibers. They can be platelets. They can be particles. You can mix different ones together. So basically, you can put together whatever you want to try to create a new material that has properties that you desire. And how can you predict those properties? That's what you basically want to look at, is some basic understanding of what's going to control the elastic properties of a composite that you may choose your matrix or your reinforcement. So we're going to start with a simple case of a fiber reinforced composite. And this could be, actually, doesn't have to be fibers. You're going to see where it's going to show a two-dimensional representation of this, where we have two materials with elastic modulus E1 and E2. So if we look at our picture of our material, so let's have a block of material. We're going to have not necessarily equal amounts, they're just sort of shown that way. This will be material 1, and this would be material 2. Whether this is a cross section of either spherical fibers, or this could be just platelets running into the board there. It doesn't really matter for this model. And if we look at the stress strain curve here, it doesn't matter if it's true stress or engineering stress. We'll call this material 1, call this material 2. So the slope of that curve is E1, the slope of this curve is E2. So, what's the modulus of this material? What's E of the composite?
Did you use growth next to it, so the fractional percentage of E1 plus fractional percentage of E2 equals E of E.
That's what we're gonna get, but there's a question you have to ask first.
What's the fractional percentage?
Where are you applying your force? Pull on this in this direction, it's gonna have a different modulus than if you pull on it in this direction. Or if you pull on it in this direction. So you gotta know how your force is applied. But anyways, so we wanna know what is E of the composite, which I'm just gonna use E C, E of composite. Well, one thing you can probably say is, you know, this is 2 and this is 1, E of composite is going to be somewhere between the two of them. Okay, so E of the composite is going to be somewhere in there. You know, if it was 100% 1, then E of composite would be here. If it was 100% 2, it would be there. So pretty much the elastic modulus has to fall somewhere in between the two of them. You know that. But you need to know the direction of stress or force. So with respect to WRT, right? Fiber direction. So we're going to look at 2 cases here. We're going to look at the force in the direction of fibers, and then we will look at force perpendicular to fibers. Sometimes this is called longitudinal, and this is what's called transverse. Or they may draw an axis and have X, Y, and Z, and they'll say X, you know, but they'll tell you that way. Okay, so we're going to start with the force in direction of the fibers. So again, to redraw our block here, you don't have to redraw, but since I'm off the page, I'm going to something like that. So we're going to apply a force here, or if you know your area here, from area A, you could apply a stress. And we look at our stress strain. Here's material 1, and here's material 2. So in order to work this problem, you have to have some understanding of what's going to happen when you pull on this. If you apply a force here and here, and you get some displacement, delta, it stretches. Do the fibers in the matrix stretch at the same amount? Yes, okay, we're assuming they're well bonded. So, okay, yeah, that's a big, so this is elastic behavior, so we're assuming there's no fracture or anything like that going on. But that is, assume well bonded, which means that for elastic behavior, we're not going to have any debonding or anything like that. So hopefully if you see this, if you pull here and here, both the fibers in the matrix are going to stretch the same amount. Okay? So on a stress strain curve, how do you represent that? This was some length L naught. Strain is delta L over they have the same strain, you can basically say, okay, we know that's going to be the strain in 1, and it's also going to be the strain in 2. Okay, is the stress the same in 1 and 2? Well, you can see right there it's not, right? What's the stress in 1? That would be the stress. Stress in 2 would be there, and this would be the stress in material 1. So this is what we call an isostrain model. It's also known as a Voigt model. V-O-I-G-H-T. After some guy named Voigt who did this math. So using this knowledge, we then can predict the behavior of the composite. So using this geometry, we can say the force supported by the composite, Fc, is going to be how much force there is carried by 1 and how much force there is carried by 2. F1 plus F2. You know that stress is force over area. So force is equal to stress times area. And if we say that using this, we can say stress in the composite is equal to the area of the composite plus stress in 1 times the area of material 1 plus force in stress in material 2 times the area of number 2. We also know stress is equal to elastic modulus times strain. So looking at this, you can see there's A1 there. This would be, if you summed all the areas, that'd be A1. Summed all the areas, that'd be area of material 2. Plug into here. You now say that E in the composite times strain in the composite times, that's our stress, area of the composite is equal to elastic modulus of 1, strain in 1 times area 1 plus elastic modulus 2, strain in 2 times area of 2. But we know from here that strain in 1 is equal to strain in 2, which is equal to the strain in the composite, right? They all stretch the same amount. So you can there cancel out your strains. And there's another proof that you can show that area fractions are equal to volume fractions. So an area fraction would be the A1 over area of the composite. And we're going to say that is equal to the volume fraction of 1. Area of 2 over area of the composite is equal to V2. And based on this, you know that V1 plus V2 is equal to 1. So volume fraction, yes?
Is the stress just different in the 2 materials because the force is being applied directly to material 1? Or is there another step?
It's because they have different elastic moduli. Because they're both stretching the same amount, but it's like having 2 springs, a stiff spring and a soft spring. If you pull on them equally, the majority of the load is carried by the hard spring for a certain amount of displacement. So that's what's in this one is. So that's a strong spring, that's a weak spring. So for the same amount of stretch, the stress is higher there. Therefore, and again, how much of the force is carried depends on how many fibers there are. If there's only one fiber in this huge block of material, the majority of the force may be carried by the matrix, but the stress in the fiber is going to be higher than the stress in the matrix. So again, you got to normalize it by the area. So different ways of looking at that. All right, so using those and plugging that in, you then can solve for E of the composite, what they're trying to get. So E of the composite is equal to E1 times A1 divided by AC plus E2 A2 over area of the composite. So plugging these in, so you always basically divide it by area of the composite there. You know that E of the composite is equal to the elastic modulus of material 1 times the volume fraction of 1 plus elastic modulus of 2 times volume fraction of 2. So now you can determine what your elastic modulus would be, and now if you make a plot of, this is not a stress strain curve, this is volume fraction here from 0 to 1, and this is the elastic modulus of the composite. If the is 0 volume fraction of 1, what's the elastic modulus of the composite going to be? E2, right? Because V2 is equal to 1, V1 is equal to 0. So that would give you E2 there. Likewise, if you know it's 100% fiber, the elastic modulus would be that of E1. And this is just a linear relationship. So this is the equation of that line. This is what we call an upper bound solution. You can't get an elastic modulus higher than this using these two mixture materials. It's gonna, it could be lower there if the alignment was off or something like that, but that's the highest modulus you could get by mixing two materials together and having the fibers all perfectly aligned, and you're pulling them, exactly in line to those fibers. So that gives us one solution for the direction in the force in the direction of the fibers. Any questions on that? So let's look at the next solution, which is force, what do I call it? I need the same thing, force perpendicular to fibers, okay. Or we say transverse. And this is what's called the Roos, if I say his name, model. So if we draw the same block of material, material 1, material 2, a straight line of course, stress, strain, and we have material 1, we have straight line, material 2, and now we pull on it this way. what can we say about the physics of this and how the deformation and the stresses are distributed here? If we pull on it this way, we're going to get some change, delta. Does material 1 stretch the same amount as material 2? Not this. What would be the same in there? Stress or force, is how you want to talk about it. Remember your free body diagram, right? You can take a cut through there, and the force has to be transferred across there. Okay, so this case, if the have the same force, and you know, of course, stress is force over area, that's going to be constant. So in this case, you draw a horizontal line this way. And that's going to be the stress in the composite. And the stress in the composite is going to be the same as the stress in the fiber. So sigma composite is equal to sigma 1 is equal to sigma 2. Based on that, you can tell me what the strain in the fibers are and the strain in the matrix. So you would draw just your, so this would be strain in 1, and this would be strain in 2. So we're pulling this way, again, you can think of these as springs. If this was a stiff spring and this was a soft spring, you pull on it this way, the soft spring is going to stretch more for a given force than the stiff spring. Higher strain in 2 than 1. Okay. This is what's also known as an iso stress model. Okay, it's the same stress across here, but you get different strains. So based on this, you can, again, come up with some math, because we want to know what is E of the composite as a function of volume fraction of 1 and volume fraction of 2. So if you were to make a composite and you needed to have a certain stiffness, okay, I'm going to choose these two materials. How much of each material do I need to use to get stiffness in this direction? That'd be an example of how you might use this. Okay, so we know we have uniform stress. And if we look at how much this changed, so if this was some length of the composite, C here, it changed, and we got some delta L from the application of that force, same with the delta there. We would say change in length of the composite is equal to the change in lengths of material 1 plus change in length of material 2. We know that strain is delta L over L naught. So delta L is equal to L naught times strain. So basically we can plug that into here and say change L length of the composite times the strain in the composite is equal to L1 times strain in 1 plus lengths of 2 times strains in 2. And of course we know that stress is equal to elastic modulus times strain. Therefore strain is equal to stress divided by elastic modulus. So substituting those in, you can say stress in the composite over elastic modulus of the composite. We're trying to get elastic modulus into this equation so we can solve for it. Times LC is equal to sigma 1 over E1 times L1 plus sigma 2 over elastic modulus of 2 times sum of the lengths in 2. And since this is an isostress model, we know sigma 1 is equal to sigma 2 is equal to sigma composite. You can cancel that out. And similarly to area fractions, we know that length fractions are proportional to volume fractions. So if you take L1 over LC equal to the volume fraction of 1, L2 over LC equal to volume fraction of 2, and of course V1 plus V2 is equal to 1. You now plug those in, and you get 1 over E of the composite. And you divide by LC here, so put that there, put LC is equal to L1 over LC E1 plus L2 over LC times E2. Therefore, if you put that in terms of volume fractions, 1 over E of the composite is equal to V1 E1 plus volume fraction of 2 E2. You can rearrange that and have E of the composite equal to E1 times E2 divided by V1 times E2 plus volume fraction of 2 times E1. And now if you plot that, volume fraction of 1 from 0 to 1 with elastic modulus. If you have 0 volume fraction of 1, what's the E of the composite? It's the same as the other answer, right? It's E of the E2. Has to be. If it's 100% 1, what's the volume fraction of it? Volume fraction of 1. So this, alright, E of 1, oops, E2, E1. So the volume fraction of 1 is 100%. The elastic modulus is going to be E1. That make sense? Same thing we did before. But now, this isn't the equation of a straight line. It's something that looks more like this. So that's how the elastic modulus of the composite, EC, will vary with volume fraction. So this is the lower bound limit. And again, if you drew the other one on there, so this is E of the composite in the longitudinal direction. This would be E of the composite in the transverse direction. So you see there's going to be a significant difference in the elastic modulus of your composite according to what direction you pull on. Any questions on that? So, yes.
So,
just to clarify, we know that the E of that composite is always going to fall between those two curves, regardless of composition.
Pretty much, regardless, it's always gonna be somewhere between here and here, regardless of the orientation. So if you pulled on it 45 degrees, it's gonna be somewhere between there. It's not necessarily gonna be half. There's more complex math you have to look at in doing that. But that's been done, and if you take a composites class, you'll do all sorts of matrix math and calculate all those things in the different directions. This is just a quick, two simple cases that give you the stiffest the composite could be and the lowest elastic modulus the composite could have as a function of volume fraction. So I think, one thing, besides this, fairly simple math, understanding this, understanding that, I think it's a really important concept for you to understand the difference between isostress versus isostrain, and how you could use that to predict what's the stress in a fiber, what's the stress in a matrix, things like that.
So when Boeing makes carbon fiber reinforced, they do panels in many different directions.
Yep.
And does that unify the stress in all directions? And where
Sort
does
of.
it look like on that?
Sort of. Again, it depends. It's often they use what's called a quasi-isotropic layup,
Okay.
where they have fibers in 0, 90, and plus and minus 45. And so if you have an equal volume fraction of fibers in all those directions, then in the plane of that composite, you see your fibers are running like this. Yes, you have fairly equal modulus in the plane, but if you pull on it in this direction, there's no fibers in that direction. So then you would be closer to this solution. So again, and then if you pull that at some angle outside of that, it would again be somewhere in between. So yes, that's one nice thing about these composites is you can, well, if you want it to be the same in all directions within this plane, you could do the quasi-isotropic. But say you have an airplane wing, okay? The stress in the airplane wing isn't the same in all directions. It's much more in this direction than it is in this direction. So you can tailor your material to have it stiffer in this direction by having more fibers here than in this direction. And that gives you a significant weight savings. So that's with the composites, you can design your material to have specific stiffnesses and strengths in different directions, which is a real nice capability to have. So that's one of the advantages of composite materials. You can engineer it to have the properties you want in the directions you need, as opposed to aluminum, which we assume is isotropic. Well, you have to have enough aluminum in there to have the stresses in this one, but you're not taking full advantage too much in this direction. So that's why it's nice to be able to use composites in certain applications. Okay, so this is the lower bound limit, and again, to make sure you understand isostress versus isostrain, and stress, strain. So isostress means you have same stress, but you have different strains. And isostrain you have the same strain, but different stresses. So, for example, you have a problem, here's a composite. The composite is stressed in this direction. What's the strain in the fiber, and what's the strain in the matrix? So, depending on what I think I gave you one of those, can you figure out this or this? So being able to manipulate those for the different materials to understand how that affects how the deformations occur, are the strains the same in the fiber, you know, here's the strain in the composite, what's the strain in the fiber? Well, I gave you the direction, you should be able to figure that out, and work those type of, things just from, you know, graphically understanding that. Okay, let's just do a quick example. A unidirectional composite. So unidirectional composite means fibers all in the same direction. Often just called a uni for short. And we have 60 volume percent carbon fiber with an elastic modulus of 400 gigapascals, 40 volume percent epoxy, make epoxy resin, or we call that the matrix. Elastic modulus of epoxy is somewhere around 3 gigapascals. So, you know, I didn't show this very realistically for carbon fiber epoxy. That might be for some other composite. So relative changes there. Calculate longitudinal and transverse module. So we know that E of the composite in the longitudinal direction is E of the fiber times volume fraction of fiber plus E of the matrix times volume fraction of matrix. So that's basically just plug and chug. So it would be 400 GPa times volume fraction is just 0.6, it's not percent, plus 3 times 0.4. So you would come up with an elastic modulus, if my math is right, of 241 GPa. Modulus of, yeah.
Should that be FBVM?
Oh, yeah, sorry. Good catch. Thank you. So elastic modulus of steel, about 210 gigapascals. So your unidirectional carbon fiber in the direction of the fibers can be stiffer than steel. Modulus of steel is about 8. The density of steel, is what I meant to say, is about 8. The density of carbon fiber composites is about 2. So if you look at it on a strength to weight ratio, it's 4 times stronger than steel. So you hear these claims, oh, it's, you know, how are they making these claims? Is it on a weight basis? Is it on a volume basis? You know, so you gotta make sure you understand when someone makes claims about, oh, this is so much stronger than that. You know, spider silk is stronger than steel. Have you heard that? Okay, on what basis? A weight basis, okay? Not on a volume basis. If you had this much steel and this much spider silk, steel would be a lot stronger. But this would weigh 10 pounds, this would weigh an ounce. So if you did it on a weight basis, then you could say spider silk is stronger than steel. So you gotta make sure when somebody makes claims, it makes sense for what you're gonna do. Because you'd have to have this much spider silk to be as strong as this much steel. And if you don't have the room for that, then you can't use spider silk. Okay, so that's the same thing. E composite transverse. Use the other equation we came up with. E of fiber times E of matrix divided by volume fraction matrix times E of matrix plus volume fraction matrix times E of fiber. Plug those in, so it's 400 times 3 divided by 0.6 times 3 plus 0.4 times 400, and calculate that out, I come up with 7.4 gigapascals. So you see in the opposite direction, it's not very stiff at all. Okay, the stiffness is mostly dominated by the modulus of the epoxy, which isn't nearly as stiff as that of the fiber. So you can see in a unidirectional composite, if you're pulling in the fiber direction, it's great. If you're pulling across it, not so good. So what do you do about that? And that's what sort of we got to, is that, you know, oftentimes you need to use multiple fiber orientations to have properties needed or required in different directions. That sentence there, sorry. So oftentimes they'll have this layup of fibers in different directions to cover that. So here's some examples of where you might have two layers, fibers going this direction and this direction. You can do that in many directions so that you have the strength and stiffnesses you need in those. But this can lead to many other effects that I'm not going to go into in detail here at all. But if you actually have something like this, where the fibers are running in this direction and this direction, and then you start pulling on it, you can get twisting and different response to this material. It's not what we call a symmetric composite. Since this upper layer would be stiffer in this direction, and this one's stiffer in this direction, you pull on it here, it'll warp and twist like this. So you have to be very careful how you lay up your layers of composite so that you get sort of a balanced and symmetric layup of your fibers so you don't get warping.
Is there a stress or strain model in like the Z direction?
In the Z direction. So,
Just like up and down.
like this way?
Yeah. Or like in the top left picture up there, like just up and down. Vertical.
Yeah, vertical. Well, are you pulling, in that case, are you pulling in the directions of the fiber, or are you pulling perpendicular to the fiber? Perpendicular to the fiber. So you would use the model that we did here. That would apply for out of plane. Even though the fibers aren't all like this, you're pulling perpendicular to the fibers. So that would give you real close to the first approximation for that.
Sort of follow-up question, what about shear?
Oh,
I'm assuming the math gets ugly.
yes. Good question. So I'm trying to think how shear is going to apply for that. So if you sheared it this way versus sheared this way. I don't remember off the top of my head what those are, but it's more complex. So this was for continuous fibers running throughout the length of the composite. A lot of times your composites can look something like this. You can have fibers that aren't continuous. You can have shorter fibers that aren't continuous. You can have fibers that are oriented in all these different directions. How does this then apply to those? It's a bit more complex. You have to understand the length of the fiber. So this would be stiffer than this because you get more stress transfer. So that's what's called the critical fiber length. If the fiber is long enough, it pretty much behaves like a continuous fiber. As they get shorter, they don't. And that's partly because you're transferring stress from this matrix to the fiber. If you only have a short fiber, you only have this much, you can't grip it very well. If you have a strong one, you do this, and this fiber isn't transferring this stress to that fiber. So if you have this effect, well, you know it's going to be somewhere between the upper and lower bound. You need to have more information and more complex models. The other effect is, even if you have your fibers running like this, what if you're pulling off at different angles? And again, there's a lot of math you can do to cover that. So one way, and you have this panel, and you have your fibers all running in this direction, and you cut tension bars out. Cut a tension bar in this orientation, tension bar like this, tension bar like this, tension bar like this, and one like this, right? Then you take all these and you pull on them. You generally get something E of the composite as a function of angle. So if we call this 0 degrees here, we call that 90 degrees. You get something that looks about like that. Actually, it drops a little bit quicker. And so this would be 0, and this would be 90. So this would give you E of the composite and the transverse. At 0, it would be E of the composite longitudinal, and let's see, 30, 45, and 60. So you get a pretty fast drop off. So at 45 degrees, E of the composite is not half of what it is. It's about a third of it in the other direction. So it's a nonlinear relationship there, and it drops off pretty quickly. And so this is what is called the rule of mixtures. And there's again the two models. There is the Voigt and the Roos model. If you remember, if you've had double E and you've done resistance of a series of resistors, you can do that whether the resistors are in series or parallel. Same math. So if you've seen this type of thing before. It goes for other properties as well. So you can use this for things like density, sometimes for strength, electrical conductivity or resistance, thermal, conductivity. So you can see, depending on what makes sense and which model you apply, you can do that. Density is pretty much always just the Voigt model. You can, density of this and density of that, you mix them together, it's just going to be the linear rule of mixtures. But things like strength, electrical conductivity, thermal conductivity, and other properties, thermal expansion, can also follow these. If you think about thermal expansion in this direction, it's going to be different than the thermal expansion in that direction according to the properties of your material. Okay, let's brief introduction to composites and elastic properties of composites. On Friday, we're going to start going into viscoelastic properties. I'll definitely email and I'll try to get it up on the Canvas site, some material you can look at ahead of time on that, because it's not in either of the textbooks. So I'll have a separate packet for that, looking at viscoelastic properties and its dampers and springs and putting them together and understanding how when you pull on things certain ways, what the time dependent response is.